All right, so let's finish up our notes here over standard 2. So make sure these notes get into your notebook. You're going to have to draw a few pictures, but make sure everything gets there with the rest of our standard 2 notes. So the first thing to go over is this stuff about transformations. So if I have a function f of x plus 1, what that does is it takes f of x, that's the original graph here, and it moves it to the left one. F of x minus 1 would move it to the right one. So let's compare a couple different integrals. Say I have to take the integral here, f of x plus 1 dx. So that's the area under that curve, let's say from 0 to 1. Let's say that's the area under f of x plus 1 from 0 to 1. So I'll shade that area in here real quick. As you can see, it goes off of my picture, but you've got the main idea. Now, how does this compare to area under the curve of f of x? Well, everything got shifted to the left one. This whole, where's my mouse? This whole function here got shifted to the left one. So the area under f of x over here that I'll highlight right now, it was originally from 1 to 2, is now shifted over, so it's from 0 to 1. So the area under the curve of f of x, area under the curve of f of x from 1 to 2 is the same as the area under the curve of f of x plus 1 from 0 to 1. So when you've got a problem and it deals with one of these functions shifted left or right, we've got to look at where that area was on the original function. Okay, similarly, let's talk about shifting up and down. So plus 1 will take the entire curve and shift it up 1 unit. You know, minus 1 would take the entire curve and shift it down 1 unit. So if I've got the area, let's say I'm doing area under f of x plus 1 from, let's go again from 0 to 1. From 0 to 1 here, that's this area. Now, I drew the box a little separately. That's part of the area as well. Because as we'll see, how does that compare to the area under, I'm going to make this a little smaller. So, there we go. We want to compare this then to the area under the curve before. Well, if we look here, this part matches up perfectly with that part. So it's equal to the area under the curve of f of x dx. Plus there's another little chunk there. There's another little 1 by 1 box. And the way this works, actually, we can use something we learned with antiderivatives, is that if we have an antiderivative and we have two different parts, two different terms, and they're split by a plus sign or a minus sign, we can go ahead and take the antiderivative of each one separately. So I can go ahead and do this with area as well. So plus the area here of 1 dx. And if you find the area under that section, you'll find that you get an area of 1. Or you can think about how many boxes it's added or subtracted when you do that. All right, let's move on to a different transformation. So absolute value of f of x. Now, if I take a function, here's f of x over here on the right, and I take the absolute value of the function, what it does is anything that was below the x-axis, so that's this section here, right there, anything down there, that gets flipped over the x-axis and becomes positive. So like this. So let's say, for instance, that we're doing the integral from -1 to 1 of absolute value of f of x. How does this relate back to the original function, just f of x? All right, I'll draw in the area right here. Okay, well, part of that area relates back perfectly, this section right here. So the area under f of x from 0 to 1 was exactly the same. Now, with the other half of this function, the other half of the area, what we had to do was flip the curve over the x-axis. So we just need to put that into our equation, and we flip a curve over the x-axis by doing -1 times that curve. So this section from -1 to 0, we need to do the area under negative f of x. Now you could write this in a couple different ways. You could make it integral from 0 to 1 of f of x and then do minus integral from -1 to 0 of f of x, or you can leave the negative sign in here. Either way works. All right, let's move on. Okay, so set up some definite integrals that would calculate the area of each region below. Once again, you probably want to sketch these pictures in your notes so that your notes actually make some sense. So this first one, we're going to set up an integral that would calculate that area. So integral, I'll always just go ahead and do it dx since we see that our variable's x here. It's hard to see, but it's down there on the x-axis. Now we're going from here to here, so that's from 0 to 5. And then what function are we doing the area under? Well, it's a constant function. It's this one right here. And that function is just 1, 2, 3, 4. So we're doing the area under the curve, y equals 4, or f of x equals 4, from 0 to 5. All right, now over here, this is where it becomes important that we know a bit about what our functions look like. Now, this function that looks like a v with a point, that's an absolute value function. But this one somehow is flipped over. It's the blue one right here. This is an absolute value function. It's flipped over. It's moved up. So let's go through the sort of transformations that got us there. So just absolute value of x, well, that just looks like this. Origins at 0, 0. Mine's not perfect, but you get the idea. Well, in order to flip it over, I do negative absolute value of x. So let's see what that looks like now. That looks like this. Origin still at 0, 0. And now I want to shift it up. So we've got to know transformations. It looks like, according to our graph, it was shifted up 1, 2, 3, 4 units. So it becomes negative absolute value of x plus 4. Gets me that graph right there. Let me make that a little better, a little more accurate. Closer. All right, so that's the one. That's how we get what we want. So this function here is y equals negative absolute value of x plus 4. So I want to write an integral to calculate that area of that region. So I'm going to do the integral dx again. And my function I've already figured out, negative absolute value of x plus 4. And then now I've got to figure out the endpoints of my integral, where I'm starting to do the area, where I'm ending at. So I look down here. I'm going from, it looks like -4 all the way up to 4. Great. So right there is our answer for that one. All right, here's our answer for this one. We weren't actually asked to calculate the area here, just to set up an integral that will do it for us. All right, let's move on. Next example. Sketch and shade the region whose area is given by this definite integral. Use geometry then to actually find the area. Okay, let's start here with A. So from -2 to 0, under what function? 2x plus 5. So we've got to know what that function looks like. Well, that's going to be a line. So I'm going to go ahead and use the line on here to make that. Plus 5 means a y-intercept of 5. And then I've got to draw it with a slope of 2. So I think that is right there, has a slope of 2. Okay, so that's my equation. That's the thing I'm finding the area under. Let's go back to full screen. I'll go ahead and shade in the area because we're going from -2 to 0. Being super careful not to go too far there. All the way up to 0. All right, and we're going to use geometry to find that area. So this shape here is a trapezoid. So its area is 1/2. Now the two bases are, this is just like when we did trapezoidal Riemann sum, so this shouldn't be too complicated. I'll do the long side here as the first base. That has a height of 5. And the short side over here is the second base, which is 1. And then the height is the distance between the two bases, which is 2. So this area equals 6. So the definite integral equals 6. Now, one thing to note, I made a mistake way back in the beginning of saying that you should put units squared after this. Just stop doing that. Just don't put units squared. It's technically, I think, incorrect. So the answer to this definite integral is 6. Okay, let's skip down and do letter C, since this absolute value one is similar to the last example we just did on the last page. So letter C here, 1 minus absolute value of x. So it might be useful to go ahead and rewrite this. 1 minus absolute value of x is negative absolute value of x plus 1. This might help us to see what it's going to look like a little better. So I'm going to sketch that now on my graph. Negative absolute value of x means flipped. Plus 1 means it's shifted up 1. So there it is. Now we got to be careful here to be specific. Absolute value of x has a slope of 1 or negative 1, depending on which side we're going on. So I'm being careful to get my slopes right there, because that might affect the areas. Okay, now I'm doing the area under the curve from negative 1 to 1. I'll shade that in. So there's this chunk from negative 1 to a half. This chunk here, and this part. So this area is made up of 3 separate triangles. So I'll do the areas for those triangles. First, I'll do these 2 small ones. Now they're negative, so I'm going to do negative 1 times and half. And the base of each one is what? Is 1/2, I think? Yeah, times 1/2. And the height of each one is 1/2. Yeah, it might be hard to see on here, but I think the scale says that each of these lines is a half. So this goes a half to 1, 1.5 to 2. So that's each of the small triangles. And there's 2 of them, so I'm going to do times 2. And then for the big triangle here, so I'm going to add that area on. It's 1/2 times the base is 1, and the height is 1/2. So when I work this out, I get, what, negative 1/4 plus 1/4. So I get 0. So the answer to this integral is 0. All right, let's go ahead and do this last one now. Now, for this last one, just like all the other ones, we're going to have to draw the function first. So in the other ones, the function was a pretty well-known function. In this one, you might not recognize this function right away. So we're going to do a little algebra to help you see what function this is. So like in the first one here, 2x minus 5, what we really had was we were graphing the equation y equals 2x minus 5. So here in this one with the square root, we're really graphing the equation y equals square root of 9 minus x squared. Now I'm going to do a little fancy algebra, square both sides. So I've got y squared equals 9 minus x squared. And then I'm going to add the x squared to both sides. So x squared plus y squared equals 9. Hopefully this is ringing some bells now. You've seen equations like this before, either in Algebra 2 or in pre-calculus, and you know that this is the equation for a circle. A circle, because the equation for a circle, and you might want to, excuse me, you might want to write this down, is that x squared plus y squared equals r squared. And so this is a circle with radius 3. And if, for instance, this was like an x plus 1 squared, that would move it to the left one, just like all of our other transformations here. Now, one thing that's important is that since we just have the positive square root, we're just going to get the top half of the circle, like this. Now, if the problem was changed, this might be something also to make a note of. If the problem was changed so that it was, gosh, it's hard to write in there, negative square root of 9 minus x squared, that would just give us the bottom half of the circle right there. But for this problem, we've only got the top half. So we draw in our semicircle from -3 all the way up to 3, centered at the origin there. And the question asks us to find the area under that curve. So let's use what we know about circles and the fact that it's a half circle to find this area. 1/2 pi times the radius squared. So we end up with this integral being equal to 9 pi over 2. Okay, fantastic. All right, there's actually just one last thing to talk about in Standard 2 that might be important for you. And I want to remind you what an even function is and what an odd function is. All right, an even function is reflected over the y-axis. Reflected over y-axis. So let's give ourselves an example here. So for instance, let's say I've got, I don't know, I've got this graph here, and I spilled coffee on half of it. I accidentally destroyed this whole side of it, and I don't know what my original graph looked at because I spilled coffee over there. Green coffee, obviously, because it's all green. But I'd like to reconstruct my graph, and I know it's an even function. So I know it was reflected over the y-axis. All I have to do is take my original half and reflect it to get the entire function. This might be helpful when we're looking at areas under the curve, because I'm guessing you can see how the area over here compares to the area over here. All right, fantastic. Let's talk about odd functions. So an odd function . Odd function is reflected over the y-axis. No, not over the y-axis. That's what I just said. It's reflected over the origin. Reflected over the origin. Okay, so once again, let's pretend I've got a graph here, and I knew half of it looked like that. And I went ahead and spilled coffee all over here, so I don't know what the rest of my graph looked like, but I do know that it's an odd function. So how can I finish this graph if I know it's an odd function? Well, I know that it's reflected over the origin, so I can go ahead and mimic the graph here. And once again, you might find yourself seeing how useful this could be to know a function is an odd function when you do the area under the curve, because you can see some comparison between this area and this area. All right, that's it for the rest of notes on Standard 2. Bring those to class with you.